We are going to discuss the calculation of the depth of detachment. Consider this cross section has been created and a kink-fold geometry is seen for a layer within this pin line up to that pin line. We call it the pin line and more precisely call it as a loose line final. Where I have put the pin line, it is at the boundary between the undeformed portion and the deformed portion of the rock. So, also here between deformed and the undeformed part of the rock, the pin line is at 90 degree with the layer which is undeformed. So, also over here. Next, suppose this folding is produced above a detachment and that information is available below some depth detachment is there, and we want to find out at what depth the detachment is there. Now, for all kink folds this method cannot be applied. Suppose we already know that the detachment exists, then only we will apply this process. This process of finding out the depth of detachment will involve the line length balance and the area balance. Both are applied. Let us see how it is done. The distance AB and BC can be obtained, AB distance and BC distance, and can be added up. In my drawing, AB is 2 centimeter and BC is 6.9 centimeter. So, the total length AB plus BC is 8.9 centimeter. What I need to do is, from point A, I need to draw a line of 8.9 centimeter length. So, here is 8.9 centimeter. Point D is marked is equal to the AD distance. Point D has been plotted on the line. Next, we want to find out the area of the triangle ABC, which is given by half multiplied by AC length multiplied by this H is equal to half. AC length is 8.2 centimeter and H length is 1.3 centimeter. So, the area of triangle ABC is 5.33 centimeter square. From the diagram I can obtain the CD length, or I can obtain the CD length also in this way, AD length which is already obtained here minus the AC length. By any of these two means I find out the CD length to be equal to 0.8 centimeter. Now, I divide this area by this CD length and it turns out to be 6.7 centimeter. I need to draw a line of 6.7 centimeter length in this direction, normal to this line. This length DM is drawn as 6.7 centimeter. Now, I will draw a line passing through this point and parallel to this line. This line can be drawn, a line can be drawn passing through point C and parallel to the DM line, and then this pin line can be drawn here extended downward. Now, what we say is that this surface is the detachment above which there has been deformation, below which there has been no deformation, a tectonic compression applied in the past. This is, by the way, loose line initial, and due to this compression this much of area was lost and an equal area over here was gained. In other words, we mean that before deformation this was the material and there was no folding present. I repeat now, as compression applied, this is the area loss and here is the area gain. Both line length balance has been made and the area balance has been made. How much is the area of this rectangle? This area is given by CD length multiplied by the DM length. DM length is 6.7 centimeter. This was a CD length. If I multiply CD by DM, I get the area of this triangle. Now, what I have shown in terms of a kink fold, a fold with straight limb and sharp hinges can also be worked out if the fold is round hinge and need not be a circular one. Let us do that. Say this is the cross section of a folded layer, and now this time the fold is of round hinge. This portion is the undeformed layer and this portion is also the undeformed layer, therefore straight and horizontal. We want to find out the depth of detachment, considering that there is a detachment at depth indeed present. If it is not present, then we cannot run this process. We need to know by some other way that there is a detachment indeed present. Our approach will be same as what we did earlier. A repetition can be useful so that the student can understand. Draw a pin line at the contact between the deformed and the undeformed rocks. Draw a loose line in contact with, this is the loose line final, between the deformed and the undeformed rocks. The line drawn, pin line, is perpendicular to the undeformed layer and the loose line is perpendicular to the undeformed layer. Next, we need to find out the length AB, the curve length AB. How to do that? I can break it into several smaller straight line segments, measure individually and find out the total length. Let us do that. 1 centimeter covered, next 1.5 centimeter altogether, then another 0.5 centimeter, so 2 centimeter from here to here, then 2.5 centimeter, 3 centimeter, 3.6 centimeter, 3.6 centimeter, and now we are going to add 0.7 centimeter, then we will add up 1 centimeter, then another 0.5 centimeter, from there another 0.5 centimeter, and then finally the last 0.5 centimeter. So, the total curve length AB is provided by summing up these numbers, which is equal to 6.8 centimeter. Unfold this layer as AB dash line. That means from A I have to draw a line of 6.8 centimeter length, and actually on this drawn line itself, and here is that point B dash. So, the AB dash line length is equal to the curved length AB length. From the diagram we can find out the BB dash length, which is equal to 0.9 centimeter. Now, I have to find out the area of this irregular geometry. To do that, I have to divide AB line into several smaller linear segments. I take the interval of 0.5 centimeter, I put several dots at 0.5 centimeter interval. Next, I draw normals on the AB line at those points. We have created how many lines? 1, 2, 3, 11 lines. We have to find out the sum of the lengths of these 11 lines. This is equal to 13.4 centimeter. The average height is 13.4 divided by 11 plus 1, 12 is equal to 1.1 centimeter. Therefore, the area is given by 1.1 multiplied by the AB length, which is 6 centimeters, which is 6.6 centimeter square. This area is now divided by the BB dash length, which is 6.6 divided by 0.9, which is equal to 7.3 centimeter. So, we draw a line from B dash downward of 7.3 centimeter length. This point is Z and B dash Z is equal to 7.3 centimeters. Next, we draw a line parallel to this line passing through the point Z. Extend the pin line downward, extend the loose line final and recognize this line as a loose line initial. Now, we say that this depth, which is same as BZ, which is equal to 7.3 centimeter is the depth of the detachment. So, what has been considered implicitly, that the area loss due to this compression moving on the detachment, this is the detachment below which rocks are undeformed, over which rocks are deformed, this is the area loss that has happened, and because of this push here is the area gain. Now, this 7.3 centimeter is the depth of the detachment as per the sketch. There must be a scale given that 1 centimeter in your sketch is equivalent to x meter in the field. Apply this scale and find out for 7.3 centimeter depth how many meters in the field, and that is the answer. The same thing has to be done when you are dealing with folds of other geometry such as the kink folds. Here we obtained the dm distance as 6.7 centimeter. There might be a scale given here as 1 centimeter in the diagram is equivalent to y meter in the field. Applying that scale, 6.7 centimeter is equivalent to y dash meter in the field, and this is the answer, the depth of detachment. So, in this way, whatever be the fold geometry, be it a kink fold, be it a round hinge fold, we can find out the depth of the detachment, provided the detachment exists, and that information has to come from some other studies. Now that this is done, we are moving to finding out the dip direction of the detachment. The approach is similar.